We're going to move on to application of series, and we're going to look at some power series. A power series is a series in this specific form. We've got some coefficients. The coefficients are the c's here, and then we have x to the n power. So this sort of thing kind of reminds you of a polynomial. If you had cut this series off and just looked at a finite sum, then it would just be a polynomial. But if you let all the c coefficients be all just 1, then it would probably remind you of a geometric series. And depending on what x is, it's either going to be a convergent geometric series or a divergent geometric series. We can kind of expand this and look at the next series, c sub n times x minus a to the nth power. We call this the power series centered at a, or the power series about a. So it's kind of, you can kind of imagine like a shift by a here. So what do we want to do with power series? What we want to know is, when does a power series converge? So that is, what x values will allow this function, we can kind of think of this as a function, what x values will this function be defined? So here we have an example. For what values of x is the series convergent? We have all of the tests available to us from the last several sections. So let's use the ratio test on this one. And so we'll take the limit as n approaches infinity of n plus 1 factorial times x to the n plus 1 divided by n factorial x to the n. And here we can rewrite and simplify. This gives us the limit as n approaches infinity of n times 1 times n factorial times x to the n times x to the first over n factorial times x to the n. Writing it like this allows us to simplify some stuff here. And now we have just the limit as n approaches infinity of n plus 1 times x. So the question is, what can we let x equal in order for this limit to exist? Well, the only way that this will exist, since this part is getting very large, the only way that this limit will exist is if x is equal to 0. So what we say is this series converges when x equals 0. Because remember, for the ratio test to converge, the limit has to be, the absolute value of the limit has to be less than 1. So the only way we could do that is if x is 0. Next, for what values of x does the series converge? Again, we'll try the ratio test, and we're looking at the limit of the a sub n plus 1 term divided by the a sub n term. I'm just going to skip to the step where we multiply by the reciprocal. Now we'll split the top up. So that we have x minus 3 to the n times an x minus 3 times an n over n plus 1 times x minus 3 to the n, allowing us to cancel here, and we've got the limit of, let's write it in the following form, n over n plus 1 times x minus 3. And then, since this first part is an indeterminate limit, we'll just do a little bit of algebra. Multiply the top and the bottom of that fraction by 1 over n to give us 1 over 1 plus 1 over n times x minus 3. So this limit now can be evaluated, and this will evaluate to 1. So all that's left will be our x minus 3. In order for the ratio test to work, we need the absolute value of this thing, which I have neglected to write this whole time, but it is absolute value, needs to be less than 1. So if I solve the absolute value of x minus 3 has to be less than 1, what that means is we've got to have x minus 3 to be between negative 1 and positive 1. Solving for x, adding 3 to all three sides of this inequality gives us 1 less than x less than 4. So now we know that this is convergent between 1 and 4. But we still need to check whether or not this works out at 1 and at 4. Did I add correctly? No. 3 plus negative 1 should be a 2. There we go. That's better. From 2 to 4. So what happens when x equals 2? When x equals 2, what do we have? We have the sum of 2 minus 3 is negative 1 to the n over n. And this is an alternating series. So actually alternating harmonic series, which we saw previously, and it converges. So let's put a check next to x equals 2. When x equals 4, then we have the sum of 4 minus 3 is 1. 1 to the n is still just 1 over n. That is the harmonic series, or a p series where p equals 1. And we know that that is divergent. So we'll put an x there. So our interval, or our values of x, for which the series converges, is from negative 1 less than, not negative 1, there we go, 2 less than or equal to x less than 4. And that's our solution for that one. So for a lot of these, you're going to have to do some kind of ratio or root test, look at the values of x that will keep the limit between negative 1 and 1, and then test the endpoints of that interval.